All right. Good afternoon, everyone. So, oh, by the way, hold on. Let me check ko lang yung audio ko. Okay lang ba? Okay, there you go. It should be okay. So, good afternoon, everyone. And so for today, we'll continue our discussion about the bisection method, and hopefully we can finish module number 2. But before that, I would just like to say something I forgot last time. So, di ba may usapan tayo na if you will not be able to make a deadline for a particular laboratory exercise, then it will be great if you can tell me one plus or minus 1 week before or after the set deadline kung hindi kayo mapagpasa. The reason is so that makapagbigay ako ng answer key, all right? And then second is para mag-guarantee na I will allow you to do the same exercise. Because one of the things that I'll try to implement this semester is that kung masyadong malayo dun sa actual deadline, yung pagsasubmit nyo ng exercises, I reserve the right to give you another set of exercise different from what was due before. Kasi nga, ilalabas ko na yung answer key. I will probably discuss the solution in front of the class if there are common mistakes or errors. All right. So yeah, and then I don't want to prevent you from coming to class. So yun, magsabi kayo kagad because if it will be more than 1 week after the deadline, then I will probably give you a different set of questions. Okay? Clear ba yun? Naririnig nyo naman ako, di ba? So hindi lang kayo nagre-react. Okay, so I hope that's okay. So again, beyond that part, so makeup exercise. So ayoko namang masayang yung effort nyo na nagawa kayo ng exercise, malalaman nyo lang later na iibahin ko pala yung tanong or I'll give you a different set of functions or different set of scenarios. So sana clear yon. And then for those who missed the laboratory classes last Monday, we started talking about the bisection method because I just realized super late na, no, natapos ko nang isulat yung schedule ng klase and the laboratory exercise that Friday would be a holiday. So February 25th, People Power anniversary. So we will not meet. Pero sinimulan ko na last Monday yung discussion about the bisection method. Right? And then for today, tutuloy ko lang siya. Tapos sana matapos natin yung module number 2. Okay? So with those out of the way, so probably we can start our discussion. I'll just do a quick recall. So last time we introduced the problem of solving nonlinear equations. So we might have some equation of the form f of x equals g of x, all right? So ito yung isang example ng isang equation. If either f or g contains nonlinear functions, okay? Or pwedeng silang mga transcendental or higher degree polynomials, then this equation, let's call it equation 1, is an example of a nonlinear equation. And then the goal of Math 175 is to provide us with the ways, at least numerical ways, in order to find the solutions x of equation number 1. And then we can translate this problem into a root finding problem. So we simply just need to make one of the sides of the equation equal to 0. All right. So pwede natin itong i-let to be our function h of x equals 0. So the problem of solving equation 1 is the same or is equivalent to finding the roots of the function h. So kaya interchangeably ko gagamitin yung solving nonlinear equations and finding the roots of an equation. So there will be scenarios that I will give you problems such as equation number 1 or in the form of equation number 1. And then para ma-apply yung bisection method, yung regular fallacy, and the iterative methods that we will discuss later, you need to first transform it into a root finding problem in the form of problem number 2. And it's just quite easy. You just make one side of the equation 0, and the non-zero side of the equation will be your function h, which would be nonlinear in nature. Okay? So last time, pinag-usapan natin yung unang method, which is a bracketing method or is an interval method. And that's the bisection method, which is actually very simple. So kailangan mo lang mag-start sa isang, kung given ka ng isang nonlinear function, so drawing ko madali. So if this is my function y equals f of x, I just need to find an interval on which I am sure that there exists a root. And for the bisection method, we need to choose that interval to be large enough so that it will contain a root. Tapos para mag-guarantee yun, dapat magkaiba yung function value nung left at saka nung right endpoint. So if A is the left endpoint, B is the right endpoint, then I'm looking for an interval AB such that f of A and f of B will have opposite signs. All right? So halimbawa, ito si A, ito si B, and clearly f of A is positive. It's somewhere here. Okay, ito yung f of A. And f of B is somewhere here. F of B is negative. They have opposite signs. So by the intermediate value theorem, I am sure that there exists a number R between A and B such that f of R is equal to 0. Provided f is continuous, right? Continuous yung function, magkaiba yung sign ni f of A at ni f of B. So therefore, si 0 ay nasa pagitan ni f of A at ni f of B. So sure ako, by IVT, there exists a root between A and B. And the goal of the bisection method is to find that value of R. Okay? So how does the bisection method works? Kukunin lang natin yung kalahati ng interval. Tapos, titingnan natin, bawa ito si C, titingnan natin yung function value ni C. Tapos, papalitin ko yung interval. I'm gonna choose either the left half from A to C or the right half from C to B. Tapos ang criterion ko sa pagpili ay dapat opposite yung sign nung magkabilang endpoints. So in this case, f of A and f of C have the same signs. So ibig sabihin, hindi ako guaranteed na may root doon sa pagitan nila. But graphically, we are sure of that. But kung magkapares kasi yung sign, hindi gagana yung IVT. Hindi natin malalaman kung meron o walang root. But I will ignore this interval because again, I'm not sure if there's a root over there. So I'm gonna choose to retain the new interval, C comma B. All right? Kasi doon merong opposite sign yung magkabilang endpoint. And we will do this repetitively until either we reach the maximum number of iterations or yung length ng interval na kinoconsider natin at that step is less than the threshold epsilon that we have set in the beginning. All right. So nangyayari sa bisection method, kinakalahati natin ng kinakalahati yung haba ng interval, and at every step we are making sure that the interval retained will contain a root. And again, the criteria is dapat magkaiba yung sign ng mga endpoints. And we are sure that this method will always converge to a root. Kasi paulit-ulit lang natin siyang gagawin at every step of the way, we know that there is a root in the interval that we will get. And then yung haba ng interval ay nangangalahati ng nangangalahati. So the length of the interval will approach 0. So definitely we will get to the root. Only problem is medyo mabagal yung pag-converge dun sa root. Okay? But nevertheless, we know, or some of the facts that we have established before, aside from the convergence of the method, it will always converge. It will converge with the rate of 1 over, at an order of big O of 1 over 2 to the n, meaning the bisection method will converge to the actual root as fast as how 1 over 2 to the power n converges to 0. Yan yung order. And we have an error estimate. The difference between the actual root and the approximate C sub n at the nth step is bounded above by b minus a all over 2 to the power n plus 1. Okay? And then this information here will give us a way on how to estimate ilan kayang iterations yung kailangan para ma-achieve ko yung isang error level. So we will look at an example of that later. So basically, that's what we did last Monday in 5 minutes. So I hope this is clear. Kahit mabilisang review lang. Okay. Now we'll pick up where we left off last time, and I'm here. Here I'll try to give you another measure of convergence. Okay. So we all know that the bisection method now converges as at an order of big O of 1 over 2 to the power n. Now another measure of speed of convergence is what we call the rate of convergence. So we say that a sequence of x sub n's converges to L with the rate of convergence L if and only if we can find a constant greater than 0 such that this limit given in equation 2.6 is equal to m. All right? So ang ang rate of convergence niya ay q if the limit of the difference between the the absolute error of the n plus 1 estimate all over the absolute error of the nth estimate raised to the power q is equal to a constant m greater than 0 as n approaches infinity. Okay? So in this case, again, q is the rate of convergence and m is called the asymptotic error constant. Okay? So titingnan natin kailan magiging proportional o anong power nung previous absolute error ang magiging asymptotically proportional dun sa bagong absolute error. Okay? So, and here, ano yung mas maganda sa tingin nyo? Mas malaki si Q or mas maliit si Q? So, kunwari hindi nyo pa nakikita yung susunod. So, what do you guys think? Which will converge faster? One with a higher Q or one with a lower Q? Any guess? Anyone? Ano yung mas gusto nyo? Kung gusto nyo mas mabilis yung method, would you like Q to be higher or lower? So mga ganitong klase yung tanong sa problem sets, ano, medyo kailangan ng konting analysis.
Higher po, sir.
Okay, thank you. Si Lian ba yun? Lian Grace. Yes, I also say
Yes po, sir.
higher. Thank you, Lian. Right, we want to have a higher Q. Kasi the higher the value of Q means nagiging remember itong mga errors ay paliit ng paliit. Kasi we already said that x sub n converges to L. So that means this guy is small, all right, because n approaches infinity. So this guy is less than 1, between 0 and 1. This guy is between 0 and 1. Tapos ang sinasabi nito ay, pwede mo itong tingnan as in the long run, ang error dun sa n plus 1 step ay proportional or almost proportional with a constant of proportionality m sa isang power nung previous error. Okay? So, ibig sabihin, kung mas malaki yung value ni Q, so ibig sabihin, mas lumiliit itong factor na to. Alright? So, mas lumiliit yung factor na to, i-multiply mo na siya ng constant, but that doesn't matter too much, saka mo makukuha yung error dun sa susunod na step. Alright? So, ibig sabihin, mas mabilis lumiliit yung error at the rate of a power of the previous error. Kasi kung halimbawa 1 lang yan, alright? So ibig sabihin multiply lang by a constant yung susunod na error. Yung error ngayon para makuha yung susunod na error. Pero kung halimbawa to ay square, remember this is a small number, so ibig sabihin mas lumiliit itong factor na to, may constant ka, so ibig sabihin mas mabilis lumiit yung susunod na error. So the thing here is we want to get methods of higher Qs. Okay? Now, see, asymptotic error constant siya lang yung proportionality constant between the new error and the power of the previous error. Okay? And then we will give some name on some special cases of Q and M. If Q is equal to 1 and M is equal to 0, all right? Meaning si Q ay 1 na pero hindi natin magawang non-zero constant si M, then this is a special case, though hindi to covered ng previous definition because the definition for the rate of convergence requires M to be positive, right? But if it so happened that Q equals 1 and yet M is equal to 0, then we see that the sequence converges super linearly. Let me see. That's super linear. And then if Q is equal to 1 and M is less than 1, then we say, hold on. I'll need to check this one. I'm not sure with this one. Should it be superlinear or sublinear? Maybe I'll Google it later. But yeah, let's just put a question mark on that for now. It might be a typo or mali siguro yung iniisip ko. Pero yeah, let me handle that special case later. Okay. But if the rate of convergence is 1 and m is less than 1, then we say that the sequence converges linearly. Kasi yung Q, parang siya yung order, parang siya yung degree nung convergence. So this converges linearly. If in the case that m is greater than or equal to 1, then we say that the sequence converges sublinearly. Okay? So, ibig sabihin, mas mabagal kasi yung m ay mas malaki kay 1. So, mas mabagal siya kesa dun sa linear convergence. If q is equal to 2, then we say that the sequence converges quadratically. Kung q equals 3, then we say that the rate of convergence is cubic. All right? And again, the higher the value of of q, the faster the convergence becomes. Okay? So tingnan natin, ano yung order, ano yung rate of convergence ng bisection method. But I have a footnote here pala before going there that the terms rate and order of convergence are often interchanged by some authors. So depende sa babasahin yung book. Minsan ang definition nila ng order of convergence ay ito. Tapos ang tinatawag nilang rate of convergence ay yung mga big O. So it's just a matter of style and preference ng author. In this case, I prefer to call this the order and Q to be the rate. Pero yung ibang authors, pinagbabaliktad nila yung tawag sa kanila. It's not a big deal. I will not penalize you kung mabaliktad yon. Pero I hope we understand what we are talking about when we say linear convergence, quadratic convergence, or when we say the convergence is of order big O of, say, x to the n. So hopefully it will not create some confusion. But again, it depends from book to book. Okay. So yeah. But let's see, what's the rate of convergence of the bisection method? So to get the rate of convergence, we simply need to evaluate limits of this form. Okay. Gusto nating makahanap ng number q such that the limit of this ratio, okay, is equal to a non-zero constant. Or there's an exceptional case when this is equal to 0 for all values of q, including q equals 1, then sasabihin natin superlinear yung convergence. Okay? But the key in finding the rate of convergence is to parang manghula ka ng values ni q. Give specific values for q, usually starting from the least natural number, and then you go up. Kung 0 yung makukuha mong limit when q equals 1, then you go to q equals 2. Kung 0 pa rin yung makukuha mong limit, go to q equals 3, and so on. If wala ka talaga makita na value ni q na makakapagpa non-zero constant dun sa limit, then you can say that the sequence converges superlinearly. Okay? In the case of bisection method, we will be lucky if we'll be doing that trial and error when we set q equals 1. Evaluate natin. Ito yung error on the n plus 1 step, right? Yung error sa n plus 1 step ay b minus a all over 2 to the power step number plus 1. So here we are at step number n plus 1. Dagdagan mo pa ng isa, so ang power ni 2 sa denominator ay n plus 2. On the nth step, the error is b minus a all over 2 to the power n plus 1. Then you do your algebra, you'll get this guy. Simplify further, you'll get 1/2. And again, we're lucky because at the first try, we have seen that the limit is a non-zero constant. So here we found out that q equals 1, and we have m equals 1/2, which is less than 1. So in this case, we can conclude that the bisection method converges linearly. But however, we don't want methods that converges just in a linear rate. So gusto natin mas mabilis sana yung convergence. Okay, so we'll keep this in mind, and that's why I'm saying that I can say that one disadvantage of the bisection method is that it is spectacularly slow. Ang advantage niya, sure tayo, lagi siyang magko-converge. Tapos, kaya nating ma-predict kung ilang iterations yung kailangan ko para ma-meet ang isang error threshold. The disadvantages, one of the disadvantages is spectacularly slow siya kasi linear lang yung convergence ng bisection method. All right? So any questions with that?
Sir, question po.
Yes, David.
Linawin ko lang, sir. So, pag yan nagtitingin po tayo ng rate of convergence, we keep increasing the Q until we have a non-zero value for M. Tama po ba?
Yep, that's right.
Okay po.
Medyo,
Thank you.
yun nga lang, medyo problematic yun. Siguro naisip ni David kung ano yung magiging problema. Kasi si Q, some authors will say that Q is desired to be an integer. Pero dun sa definition natin ginagamit, hindi required na si Q ay integer. Kasi yung ibang author gusto nila ay integer para masabi na siya ay linear, quadratic, cubic, quartic, or quintic, and so on, yung rate of convergence. But in practice, Q need not be an integer at all. So, medyo problematic yung paghanap. Kasi may tatlong possibilities lang naman. M is 0, M is a non-zero constant, and M is infinity. Alright? So, yun. Parang trial and error siya talaga. But again, luckily, sa bisection method, ay nakita natin na siya ay linear. But otherwise, you keep increasing Q. Now, there is a way to experimentally estimate the rate of convergence. Kaya lang, dinidiscuss ko siya dati sa chapter 1 ng Math 174. Pero nung sinulat ko yung AMAT 152 na course, nilipat na namin siya doon. So, in AMAT 152, if you can recall, there could be, or there might have been a discussion about the experimentally estimating the value of Q para hindi nyo siya para hindi kayo magta-trial error without any idea. All right? Pero if you want to take a look at it, it's in my Math 174 work text somewhere in chapter number 1. So, pero yun, for now, yun, trial and error lang yung pwede natin gawin. Okay?
Sir,
Yes,
Ques-
go ahead.
question po.
Mhm.
Yung value po ng Q, sir, ay unique or pwede kaming magkaiba ng value ng Q?
Yung value ni Q dapat ay unique. Kasi,
so yung ano po, yung answer po is yung first value ng Q na non-zero yung M. Yan po yung answer ng Q, sir.
Right. Kasi kapag meron kang value ni pag meron kang real number na hindi yun yung rate of convergence, then sure tayo na si M ay hindi magiging non-zero constant. All right? So siya ay magiging either 0, infinity, or a unique constant. Yung isang beses lang siya magiging unique non-zero constant at yon ay sa rate of convergence Q. But otherwise, sure ka na makukuha may either 0 or infinity. Okay, so kaya unique lang yung value ni Q. Isip yun yung kagabi kung unique yung value ni Q. Yeah, unique siya. Pero hindi natin siya iprove dito kasi convergence analysis na siya. Alright? Okay.
Thank you, sir.
All right. Yeah, thank you for the nice questions. I hope you keep them coming. All right. So, and then as I have mentioned, isang advantage ng bisection method ay na-foresee natin gaano kahaba yung proseso bago tayo makaabot doon sa error threshold na gusto nating makuha. And this is thanks to Theorem 2.1, wherein we prove an error estimate for the bisection method. So let's look at how it is done. Look at example 2.2. So here we suppose we want to get a better estimate for the largest root of x to the 6 minus x minus 1. Same function as we look at last time, all right? And then i-keep natin yung starting bracket or yung starting interval to be 1, 2. The question is not to find an estimate for the root, but to see at least how many iterations of the bisection method is needed so that the estimate obtained is within 10 to the minus 6 of the exact solution. At ito yung kailangan yung medyo basahin ng masinsinan yung problem at i-contextualize siya dun sa mga concepts na binigay natin. Kasi di ba, medyo magkaiba yung length ng interval, which is our interval-based stopping criterion, and the actual error. Kasi kung meron kang interval, kung yung nth interval mo ay of length, say, epsilon kunwari. Wag epsilon yung gamitin natin. Halimbawa siya ay alpha. Ang length niya kunwari ay alpha. Then remember, para makakuha tayo ng mas magandang estimate, ang napagkasunduan natin last meeting is that we will get C sub n to be equal to the midpoint of the interval of the current interval. All right. And this choice guarantees that the error minus the actual root, say r, will be less than or equal to half of the length of the interval over which we have chosen C sub n. So this will be bounded above by alpha over 2. All right? So kaya kailangan yung isipin with this as background kung ano yung gagamitin kong inequality sa problem na to. Now, if we will read the problem carefully or yung gist ng problem, kailangan nating mahanap ilang iterations, at least ilang iterations yung kailangan para yung estimate root natin ay magiging within delta units of the exact solution. So gusto natin yung estimate, but remember, our estimate is C sub n. And we want it to be within delta units away from the exact solution R. So this should signal to you na ito yung gagamitin ko. All right? Kasi ito yung distance between the estimate and the actual root. And again, we have seen in the proof of theorem, or actually in theorem 2.1, na this guy is bounded above by half of the actual interval, which is b minus a all over 2 to the n plus 1. All right? So yeah, paglalaroan ko lang yung inequality na to, right? So we want this to be true. C sub n minus r should be less than or equal to the given delta, all right? And then you plug in this value. So how do we assure that this inequality will be true? This inequality will be true if an upper bound for for the absolute error will be bounded above by 10 to the minus 6. So kailangan maging conservative tayo dito ng konti. Alam ko to ay hindi lumalampas ng b minus a over 2 to the power n plus 1. So para masigurado na itong absolute error na to ay hindi lalampas ng delta, we can impose that an upper bound for this, namely b minus a over 2 to the power n plus 1, should not exceed 10 to the minus 6. So medyo ano pa nga to medyo conservative pa. Kasi ito lang yung gusto nating inequality na makuha. But we don't know what the exact value of C sub n minus r is. All right? So that makes the computation of the exact minimum number of iterations impossible. All right? Pero alam ko ito hindi lalampas ng b minus a over 2 to the power n plus 1. So pag inimpose ko na yung b minus a over 2 to the power n plus 1 ay hindi lalampas ng delta, sure na ako na itong inequality na to ay na-satisfy. All right? So instead of dealing with this, I will look for the solution n of this inequality. Okay. The problem says that the initial bracket to be considered is 1 to 2. Yes, 1 to 2. So b is 2, a is 1. So this guy will be 1 over 2 to the power n plus 1. Magkakaroon ka nito. Less than or equal 10 to the minus 6. Play with it, do your algebra thing. You'll get this guy, and then solve for the value of n. You'll get this. All right. So this means that as long as if we want this inequality to be true, we can impose n to be no less than this guy. All right. Now the left-hand side of this inequality is around 18.9316. So this is telling us to get the to ensure that you get an error less than delta, then we must choose n to be no less than 18.9316. All right? So that means we will need at least 19 iterations, or actually hindi pala at least. Sa pang-labing-siyam na iteration, sure tayo na yung error ay hindi lalampas ng 10 to the minus 6. Okay? So that's one advantage. Isa pa sa mga advantages ng bisection method. We can anticipate how many iterations we need, and that is thanks to the error or the error bound established by Theorem 2.1. Okay, So any questions with that process? Yes, Lian Grace.
Sir, quick question lang po dun sa solution po, sa line 2 po.
Aha.
Yung inequality po sa left side, sir, yung sa leftmost part po, talaga po bang less than or equal po yun? Kasi sa Theorem 2.2 po ay less than po. So may effect po ba siya?
Wala naman siyang masyadong malaking effect kasi di ba to ay less than or equal to. Tapos sa rules of logic, pag nag-or ka, pwede kang mag-addition, right? As long as one of the statements is true. So thank you for that observation. Probably just to be safe, I'll put a less than here. Okay.
Okay po. Thank you po, sir.
Salamat, Lian. So yeah, edit ko na lang siya later. But it's not a big thing. So yeah. Okay. So yeah, here are some practice problems that you can try. Hopefully, I hope you have started writing a code for the bisection method. So kapag ka nakapagsulat na kayo ng code, pwede nyo gawin, i-verify nyo yung example 2.1. Hopefully, you get the same figures as I did. Then, kung bored kayo, try nyo yung exercise 2.1. Sa exercise 2.1, pinapa-verify ko lang na after or on the 19th iteration, yung estimate is within 10 to the minus 6 of the true solution. However, may problema pala to. No? Okay lang pala. So, ibig sabihin, titingnan nyo lang yung B minus A. I-implement nyo si bisection method 19 iterations. Tapos, dapat yung B minus A, B sub n minus A sub n all over 2 dapat ay pass ng 10 to the minus 6. If you are on the 19th iteration and the half of the current interval is still larger than 10 to the minus 6, then something might have been wrong with either your code or itong computation ko ng minimum value ni n. Actually, hindi siya minimum value ni n. Siya yung sure na value ni n. Wait. Siya yung minimum value ni n na sure ako na yung error ay hindi lalampas ng 10 to the minus 6. It can come earlier. All right? Pwedeng 5th iteration pa lang, malapit ka na dun sa error. But I know that on the 19th iteration, by hook or by crook, I'm sure that nasa 10 to the minus 6 na yung error. Okay? And then another exercise, if you are more of a fan of the theory, try to get a general formula for the least, so least number of iterations needed for the least number of iterations needed to guarantee na yung error ay hindi lalampas ng delta in terms of A, B, and delta. So bigyan nyo lang ako ng formula. Ano yung number of, para sa number of iterations. Okay? Malay nyo, lumabas to sa problem sets. So kindly try this out. Okay. Now, okay. Sinabi ko dito yung drawback. Okay. Now, another drawback of the bisection method, aside from being spectacularly slow, is that hindi niya kayang maghanap or hindi natin nakokontrol kung aling root yung makukuha niya in the presence of multiple roots within the interval AB. So basically, we cannot anticipate, right, kung saang root siya in a general fashion, kung saang root siya pupunta kung meron kang dalawa o higit pang roots sa isang interval AB. So the only remedy that we can address here if we are looking for a specific root, okay, ay tingnan talaga yung graph ng function and choose your interval AB small enough, right, na isa lang yung root doon sa interval AB. Okay? And let's illustrate it by example 2.3. So let's approximate the smallest solution of this equation, e to the minus x equals sine of pi using the interval-based tolerance 10 to the minus 6. Okay, so is there a way how we can solve this analytically? I don't think there's a way to analytically solve this, tama ba? To solve for x. Mag-arc sine ka, mag-ln ka both sides, things will get nasty. So it is a pain to solve the equation in example 2.3 by hand. So we will resort to numerical techniques. And then the thing here is, okay, we are looking for the smallest solution. Okay, Kasi marami itong magiging solutions, alright? Now, in order to see that, let's translate this equation solving problem into a root finding problem, okay? So this is an equation. Para magamit si bisection method, kailangan ko siyang i-translate into a root finding problem. Kasi ang foundation ng bisection method is finding x-intercepts, which are the roots of a function. But again, we have said this is easy. Just make one side of the equation equal to 0. The non-zero side will be your function f. And you'll be looking for the root of that function f. Now, in this particular case, we can let f to be the function e to the minus x minus sine of pi x over 2. The roots of f will coincide with the solutions of the function of the given equation. And then let's take our favorite graphing software and look at the graph of the function f over a large window or over a nice window. Right? I'll do that, and the result will be in figure 2.3. Remember, ang function natin dito ay e to the minus x minus sine ng pi x over 2 nga ba? Okay? So ito yung graph niya. Okay. So makikita natin na since may sine term dyan, ine-expect talaga natin na ito ay mag-oscillate later on. Alright? So there would be an infinity of solutions for this particular problem. Alright? But we were told to find the smallest root. So looking at this window, we can hypothesize that this is indeed the smallest root. But again, we need to make a quick analytic check to make sure that this is indeed the smallest solution. Hindi pwedeng basta mag-bisection method ka na lamang. Kailangan i-analyze natin kasi specific yung root na hinihingi ng problem, right? So the only complication that might arise here is baka bumaba eto siya later in life, right? So pag nasa kaliwa tayo, baka bumaba uli yung function, magkaroon uli ng root. But actually, that won't happen because what? For negative values of x, all right, e to the minus x will be a positive number. Actually, it would be a large positive number, at least greater than 1. Okay? So this would be greater than. It's a sine function. The sine function will have magnitude at most 1. So this guy is always greater than 1. This guy is always less than 1. So therefore, their difference will always be positive. So that means on the left of the y-axis, so for negative x's, we are sure that f will always be positive. And hence, there will be no root less than 0. And that will signal to us, okay, we can go ahead with the bisection method because graphically we know a neighborhood of the root. So ito yung gusto nating hanaping root. And again, kapag ka nagbigay ka halimbawa ng interval 0 to 5, okay? So 0 to 5 halimbawa. Okay, meron diyang tatlong roots yung function f. We cannot control how the bisection method will behave. So depende kasi kung saan papatak yung midpoint sa bawat interval at kung paano mo sinulat yung program ng bisection method. But there is no generic way on how to guarantee you will get your desired root. So the only remedy to that is to make sure to pick an interval that is small enough to contain only one root, but large enough to contain one. All right. So in this particular case, liliitan ko yung interval na i-consider ko, dapat somewhere over here lang. Hindi niya dapat makover itong root na malapit kay 2. So malapit siya kay 2. So hindi ko dapat isama si 2 dun sa bracket na gagamitin ko. All right? But again, may requirements si bisection method. Dapat magkaiba yung sign f of a at saka ni f of b. So you could choose any interval satisfying those criteria. But I guess in this problem, I used a equals 0 and b equals 1. At x equals 0, ang function value ay positive. At x equals 1, negative yung value. So ito yung x equals 1. So that's a nice bracket. It's a nice bracket because the bisection method is guaranteed to converge to a root. And at the same time, there's only one root in the interval 0, 1, as we have observed graphically. and confirmed analytically. So it's safe to use the interval 0 to 1 to get the smallest solution of the given equation. So i-feed nyo lang dun sa program nyo. Ito yung function na gagamitin natin. Tapos ang interval na pagsisimula natin ay interval 0, 1. Let your program run. And you'll get this sequence of approximates. And here, if the error tolerance is 10 to the minus 6, the interval-based stopping criterion. So titigil lang yung program kapag yung length ng current interval ay mas maliit na sa 10 to the minus 6. And you see here that it took 20 iterations before we get to an interval of length 10 to the minus 6. And again, per our convention, our estimate for the root will be the midpoint of the last interval considered. So in this particular case, we got our estimate 0.443573. Okay. All right, so let's see. Okay, so I think that's example 2.3. And then dito sa discussion, sinabi ko rin ano yung error bound, ano yung maximum possible error by choosing R star to be 0.443573. And again, the error bound would be 1/2 times the length of the interval kung saan natin pinili yung root. All right, 1/2 kasi pinili natin yung midpoint. Okay, so since we are on the we stop at the 20th iteration, the length of the original interval is 1. So that means our error bound is 1 over 2 to the power 21. So that means we are sure that the estimated root is within 4.77 times 10 to the negative 7 of the actual solution. Okay. Tapos we are lucky that in this problem, the difference between the actual root and our estimate ay maliit, and at the same time maliit din yung function value ni R star. Yung estimate natin na R star gave back a value of 10 to the minus 7. And they are almost of the same orders. Okay, pareha silang 10 to the minus 7. Unlike what we have seen in estimating the root of x to the 6 minus x minus 1, na medyo may isang order discrepancy yung function value ni R, yung function value ni R star, at saka yung actual value ni R. So yung absolute error at saka yung magnitude ng function value ng estimate ay medyo magkaiba ng order. The reason behind that is yung x to the 6 minus x minus 1, meron yung mabilis mag-grow yung function value. So pag gumalaw ka lang ng konti sa kaliwa or sa kanan ng root, posibleng mabilis yung paglaki ng function value. So that means even if your R star is close to R, the function value of R star might not be that very close to 0. Okay? Pero dito sa kaso nung example 2.3 natin, dahil yung function ay e to the x minus sine of pi x over 2 on the neighborhood of 1, okay, or on the interval 0 to 1, hindi ganun kabilis yung pagtaas or pagbaba ng function value. Kaya pag gumalaw ka ng 10 to the minus 7 to the left or to the right nung actual root, yung function values ay hindi rin lumalampas ng 10 to the minus 7 yung fluctuation. All right? So that's why this is a good example wherein a very small difference between the actual root and the estimated root gives also implied na yung function value ni R star ay napakalapit kay 0. Okay? So, yes, questions? All right, so kung walang questions, then...
Sir, question po.
Oh, yeah. Go,
Doon
David.
po sa, scroll up po kayo ng konti, sir. Ayan po, yung sa, within dun sa error natin, tapos yung function value ng R star, pag magkaiba po ba yung order niya na, bale, is that a problem po, sir?
Depende sa application area na gusto mong gamitin yung root. Kasi di ba dito ay ina-approximate natin yung root. So kung dun sa application area mo ang gagamitin mo lang naman ay yung x values. You are more interested in using the x values. Meaning, gusto mo ay maliit yung difference between the actual root and the estimated root. Then, okay itong interval-based stopping criterion. Pero meron kasi mga applications na gusto mo yung function value ng estimate ay malapit kay 0. Tapos yon, hindi natin siya na-take into account dun sa bisection method. Kasi ang bisection method, ang gina-guarantee niya lang, in the current way we wrote the code for the bisection method is magkalapit yung root at saka yung function value. Pero kasi may mga function na ang bilis nung pagbabago ng function value. So, halimbawa, ito, napaka-steep nung graph ni F. Okay. So, ito si R. Tapos halimbawa, si R star ay nandito. Yan yung estimate mo. So, in this particular case, napakalapit ni R star kay R. So, kung ang concern mo ay X value, so kung ang gagamitin mo naman si R star, gagamitin mo sa another computation other than the function value. You want to use R because it is a root or it is close, it is the root. Tapos gagamitin mo siya sa ibang computations, then gusto mo lang talaga malapit si R kay R star. That is fine. That is covered by the bisection method that we wrote. Pero kapag ang concern mo ay yung function value, gusto mong piliin si R star so that its function value is very, very close to 0, then you will have a big problem if your function grows or decays fast. Kasi kung makikita mo, ano yung function value ni R star? Ito yung function value ni R star. Medyo malayo siya kay 0, okay? Kasi mabilis nga yung pagsak ng values ni R. May sudden decrease na nangyari or sudden drop in value. So, kung si R star ay hinahanap mo, kasi gusto mong maliit yung function value niya, there would be a problem here. Kasi kahit malapit si R kesa kay R star, malaki yung function value ni R star. Okay? Pero kung ang concern mo lang naman ay dapat si R star ay malapit kay R, then okay yung bisection method. Pero depende siya from application to application. So, yeah. Kaya meron tayong iba't ibang i-introduce na stopping criterion para makita natin na depende kung ang focus mo ay dapat si R ay malapit kay R star, then the interval-based stopping criterion is fine. But if you are more concerned in making the function value of R star or finding R star so that its function value is very, very close to 0, then you need to be careful if you're dealing with functions with very fast oscillations. Kasi posibleng malapit nga si R star dun sa root, pero yung function value ni R star ay hindi ganon kalapit kay 0. Okay? Does that make sense?
Apo, sir. Thank you po.
All right. Yeah. Siguro sa problem, bibigyan ko kayo ng hint kung ano yung mas okay gamitin. Sabihin ko, concern ko dapat si R malapit kay R star. So dapat alam nyo na interval-based yung kailangan yung gamiting stopping criterion. Pero pag sinabi ko, concern ko, gusto ko makahanap ng R star na yung function value ni R star ay malapit kay 0, you can still implement the bisection method, but you need to look for another stopping criterion. Kasi kapag fast yung decay o growth ng function f, posibleng malapit na si R kay R star, pero yung function value ni R star ay hindi pa rin malapit kay 0. Okay? Now, yan. Fail na yung goal ko na tapusin yung module 2. But that's fine. At least we are learning. Let me just finish example 2.4. Hindi pala, last na to. Wala pala example 2.4. Hold on. Okay. Yeah, and David brought up a nice point. Yun yung nagiging problema, right? So kahit continuous yung function, di ba sa epsilon delta definition ng isang function, kapag continuous yung function, kapag yung given any epsilon greater than 0, making x close enough to r, okay, within delta units, then we can guarantee that the function value of f is close to the function value of r. right? So for any epsilon greater than 0. Pero yun nga, pagka merong fast oscillation, sudden drop in value or sudden increase in value yung function f, kahit na maliit yung distance between the x values, posibleng magkalayo by some order yung function values nila. Kahit continuous pa yung function natin. So that's why the interval-based stopping criterion is not always the best choice, okay, for the bisection method. So we can introduce some other stopping criteria. In fact, we will consider two stopping criteria pa. The first one is let's call it the function value-based halting criterion. So if you are more interested in making sure that the function value of the chosen estimate is very, very close to 0, and you're afraid that your function has high oscillations, then the function value-based halting criterion would be more warranted for the problem. So paano yung stopping criterion? Instead of checking how long your current interval is, tingnan mo na lamang yung function value ni C sub n. So gawin mo yung bisection method hanggang either lumampas ka na dun sa maximum number of iterations, or yung function value ni C sub n ay mas maliit na dun sa epsilon na gusto mo. Alright? So kung may code na kayo ng bisection method, per our discussion last time, you just need to modify it and change your stopping criterion. Instead of checking if the absolute value of b sub n minus a sub n is less than epsilon, you can replace it by evaluating the function value of your current estimate and comparing it to 0. Okay, tingnan nyo gaano kalayo kay 0 yung current estimate. Kaya tinawag ko siyang function value-based stopping criterion kasi titigil tayo kapag yung threshold dun sa function value ay nasatisfy na. Remember, we are looking for roots, so we want the function values to be close to 0. Okay? Now, merong mga ibang instances na, okay, function value-based criterion or interval-based criterion, kaya lang, wala nang significant change in the estimates that we are getting. Okay? So, limbawa, mag-run ka ng isang iteration, ng isang bisection method for a certain function, kaya lang napakabagal na nung pagbabago nung mga C sub n's. Alright? So, if that is the case, then we can use the jump-based halting criterion. Sa jump-based stopping criterion naman, mini-measure natin ilang percent yung pagbabago dun sa estimate. Kapag yung percent change dun sa estimate ay hindi na ganun ka-significant, ibig sabihin, bawat iteration ng bisection method o yung mga pahuling iteration ng bisection method, hindi na ganun kalaki yung pagbabago sa mga C sub n's, then it is not worth it to continue the process kasi you are not getting closer and closer to the solution anymore. Or the computational expense ay hindi na ganun ka worth it. So parang nalulugi ka na. Nagko-compute ka pa rin ng bisection method pero hindi na ganun kalaki yung iginaganda nung estimate. Now, to mathematically check if the changes in the estimates are still worth it, you can take a look at the relative change. So kunin mo yung C sub n minus C sub n minus 1, i-divide mo by C sub n. So ito yung percent change nung estimate sa bawat iteration, and check if it is within your tolerance. Salma, sabihin mo, titigil ako pag hindi na nagbabago yung mga C sub n's by 0.1%. So you can choose your epsilon to be 10 to the minus 3. Ibig sabihin, kapag masyado ng malaki si n, hindi na nagbabago by 0.1% yung mga estimates ko. So it is not worth it to continue the iterations anymore. Nagsasayang ako ng oras kasi tumatakbo yung oras pero hindi naman ganun kalaki yung iginaganda ng aking estimate. So that's the jump-based halting criterion. In some cases, you can use combinations of these. Galingan nyo lang yung paggamit ng connectives or and AND dun sa program nyo. Then you can build a perfect bisection method for a given scenario. Okay? Now, Another thing you can try is exercise 2.3. Ito ay paggamit ng iba't ibang halting criteria. Oh, by the way, if you'll be implementing the jump criteria for the stopping criterion, kailangan yung i-save yung previous value ni C sub n. Okay? Kasi kailangan mong kunin yung relative change. So, kasi meron tayong propensity na i-overwrite na lang yung mga C sub n's. Hindi natin sinesave yung mga values ng C sub n. So, kung jump-based stopping criterion, you should put a line in your code that will save the C sub n from the previous iteration para makompute mo tong ratio na ito. Alright? So, overtime na ako ng 5 minutes and yet I was not able to finish module number 2. So that means, So that means, hindi due yung buong exercise. Oh, by the way, anong gusto nyo guys? Mag-discuss kami sa lab or hatiin na lang natin yung lab exer 1.1? What do you think? So it's either sa Monday, ang gagawin nyo lang sa lab ay problems 1 to 4. Okay. Problems 1 to 4 or pwede namang 1 to 6 pero i-devote namin yung first hour discussing the regular false method. So sige nga mag-poll tayo. Raise hand kung sino yung gustong problems 1 to 4 lang yung deadline sa Monday. Walang discussion sa Monday, gagawin nyo lang yung problem 1 to 4. Sige nga, raise of hands. Majority na ba yan? 15. Okay, so I think that's the majority. Sige na nga. So sa Monday, ay gagawin lang natin yung, so sa Monday, ang deadline, ang due lang, ay yung problems 1 to 4. Okay, so Monday, so magkakaroon tayo ng exer 1.1.1.1 or part 1. So ito ang magiging due ng on Monday. So that means ang due lang sa Monday, 11:59 p.m. ay hanggang problem 4 lamang, right? Then we'll talk about the regular falsity method on Tuesday, all right? Then let's talk about when the deadline for problems 5 and 6 would be, okay? So any other questions or concerns? May questions ba? CK, may tanong ka ba? Kaya ka nag-raise ng hand.
Yes po, sir.
Yes, go ahead.
Napansin ko lang po kasi, sir, sa example 2.2 and example 2.3. Kasi po, sir, dun sa exercise 2.1, we have to verify that indeed within 19 iterations, we are guaranteed that the resulting estimate is within 10 to the negative 6 of the true solution. Kaya ako po, sir, nasabi dun is example 2.2, 2.3, same po yung length ng interval, which is 1. Tapos yung tinignan ko po sa page 11 po, yung figure 2.4, it's already at iteration 19, pero yung length po nung interval is not yet less than 10 to the negative 6.
All right. Table ano nga 2.4?
Figure 2.4 po, sir.
Figure 2.4.
Sa page 11 po.
Eto.
Opo, sir.
Ilan na ba to? 1, 2, 3, 4, 5, 6. So sa iteration 20, sa kanya naabot yung 10 to the minus 6. Tama?
Opo, sir.
Pero sa iteration 19, siya ay 0.000002. So around 2 times 10 to the negative 6 na siya, no? Pero remember, yung kinompute natin doon ay, ang kinompute natin sa example 2.1 ay, dun sa example na 19 iterations yung sagot, ay siya yung relative error. So ibig sabihin yung length ng interval yung length nung nandun sa 19th interval, kakalahatiin pa natin para ma-compute. Let me see. Baka kulang pa pala yun, no? Same function ba yung ginamit sa example?
Alin po, sir?
Ito. So, example 2.2. Same functions, no? X to the 6 minus x minus 1. Same interval 1 to 2. 10 to the minus 6.
Napansin ko lang po, sir, kasi sa example 2.2 and example 2.3, same po yung length ng interval. Kaya doon po ako nag-compare sa minimum number of iterations.
Right, kasi parehas yung ano nila, no? Parehas yung nasa problem, doon sa problems na yun. 2.3, 2.4. Okay. Tapos dito. Yeah. Hindi ako sure kasi dito ay naka 10 to the minus 6 na siya, no? 10 to the minus 6. Hindi ako sure kung ano yung eksaktong value nito. Kasi yung pinadisplay ko lang kay MATLAB ay 6 decimal places lang. So, or gantong karaming decimal places. Kaya lang sa 19th iteration, ito na yung error. Ito na yung length ng interval, right? Tapos, yung error dun sa 19th iteration ay kalahati nito. Tama ba? So, kalahati niya. So, ang kalahati niya ay yung length ng susunod na interval. So, yung hindi ko lang sure ay nag-round up na ba si MATLAB dito. Kasi ito ay 10 to the minus 6, kaya lang nasa ano siya, no? Nasa 1 times 10 to the minus 6 siya, kaya lang may truncated decimal places dun sa display. So, I will check later. I-chat kita, CK. Kung pag in-expand ko to, kasi ito yung error, no? Ito yung magiging error on the 19th iteration. Kung pag in-expand ko to, pinadisplay ko yung mas maraming decimal places. Titingnan ko kung mas maliit na siya sa 10 to the minus 6. Dapat mas maliit na siya sa 10 to the minus 6. Otherwise, may something na mali dun sa computation ko nung value ni n. Alright? That's
yes po,
sense,
sir.
Yeah. Kasi, nga, no? Kasi ito ay masyadong nasa bingit. 10 to the minus 6 lang siya talaga. Pero do we agree that ito yung error, right, on the 19th iteration? So, kailangan ko lang makita ano yung actual value na to. Dapat ito ay mas maliit sa 10 to the minus 6. So, I'm hoping si MATLAB na ground up lang, na siya ay 9 times 10 to the minus 7 or something smaller. Para tama yung sagot ko sa example, example 2.2. But I'll get back to you, CK. Iraran ko uli yung bisection ko after we hang up this call. All right? So, sorry, medyo overtime. Other questions? Nga, no? Hindi nyo na pala kailangan gawin yung exercise. Nandun na sa figure 2.4 yung sagot. Nice catch, CK. So, kailangan ko siyang baguhin later. Gawin ko 10 to the minus 8. Hindi, verify nyo nga pala. Okay, but anyway, that's fine. So, any other questions? All right, so if there are none, then thank you guys for coming today and enjoy the long weekend. And let's see each other again on yung lectures Tuesday as a Wednesday. Pero yung mga lab students ko, let's see each other again on Monday. Bye, everyone.
Thank you po, sir. Ingat po.
Thank you po.